Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 33. So we are continuing from the previous lecture where we were solving the wave equation. We were solving the wave equation given in page 2 here, right? We were already solving this wave equation, and why are we solving this? We are solving it to understand the motion of quantum mechanical systems, wherein we have to somehow give this particular species, that is the quantum mechanical system, a wave nature as well as a particle nature. As part of it, we had stopped in a stage where we had assumed that your g of t is going to be cosine omega t, and where g of t is nothing but the time part of this equation. This equation, right, u of x comma t, this u of x comma t was shown in the previous class. It was shown in the previous class that this could be separated as your f of t times g of t. And considering the oscillatory notion, right, oscillatory nature of this wave, and considering the idea that we are somehow equating second derivatives here, right? This is a very valid assumption. This is a valid assumption that by differentiating cosine omega t 2 times, right, I would be getting back the cosine function somehow, right? Yeah. So if my g of t is going to be cosine omega t, right, I will write it here, right, based on this expression right here, based on this expression, page 1. I will call this expression A, right? Yeah. Now, using g of t equals cosine omega t in expression A, I will be getting this expression A as dou 2u by dou t square, right? This is going to be, my f of x is going to be a constant, and now cosine omega t, if I differentiate it twice, what will I be getting? Again cosine omega t, right? And what is going to be happening to the omega here, right? The first time I differentiate it, this is going to be becoming an omega outside, right? Differentiating cos, the first time is going to be giving me a sign, right? A minus sign. So this is going to be minus omega the first time. The second time I again do it, this is going to be giving me yet another omega. Then, because the sign is now going to be cos, there will be a minus sign here. So this is going to be minus omega square. So this is going to be minus omega square f of x times cos omega t. All right. So this is what we have. Now we have to equate both the sides in the original wave equation, which is given in page 2 here. Okay, we have to equate both the sides. So equating LHS and RHS in the wave equation. Okay, right? Recall from the last class. See, in the last class we had obtained a term for the LHS, right? And the RHS term is given right there in page number 3 right here. Okay, right? So if you are a student taking this course online, you can, if for example this part of the board and this part of the board are not visible together, right, simultaneously, you can just go back in time. You can just go back in time for a few seconds earlier and you can see the expressions, right? And for this particular term, which we derived in the previous lecture, you can go back to this particular term there to look at the exact details. I'm going to use the final result for the derivation of this particular term right here. Okay, right? So my LHS is going to be becoming dou to u by dou x square. Okay, right? Sorry, it should be dou t square. Okay, not dou square x square and dou square t square. It should be dou x square and dou t square. All right. So I'm going to be substituting the LHS here. So this is going to be I'm differentiating with respect to x, keeping t a constant. So this cos omega t is going to be coming outside, and this is going to be d square f of x divided by dx square. Now this is equal to my recall that there is a 1 by v square term also in the original wave equation. So this is going to be 1 by v square, right, times this guy right here. So minus omega square f of x cosine omega t, right? So the cosine omega t's get cancelled out, and this equation just becomes out d square f of x by dx square is equal to minus omega square f of x by v square. Okay, right? Where omega is 2 pi nu and v is nu lambda. Are we fine with this? Okay, so this is the expression we have. And I want to draw your attention to a mistake I made in a small notation in the wave equation. The wave equation is dou square u x comma t over dou x square, not dou 2x2. Okay, I think in the last class by mistake I had also added a 2 here. So kindly, go back and correct it in your class notes. Likewise here also in the RHS, it is dou 2u x comma t by dou t2. There is no t here between t and d. That is not any part of any notation. That was just a mistake made. So kindly correct that. Okay. So please go ahead and correct it. And so the correct wave equation is given right here. I've still retained this page 2 right here. Okay. All right. So the wave equation, after making the assumption of separating the variables and followed by substituting the time part as an oscillatory cosine or a sine function. We chose a cosine function for convenience, right? We are getting this term right here. All right, dou 2 f of x by dx square is minus omega square f of x by v square. All right, let's call this expression b. Okay, I will delete this part now, and you look at expression b right here. Okay, so what did we do so far? A partial differential equation, right, which could only be solved under the assumption that the variables could be separated, right, as a product function, right? Once we did that, we transformed it and cancelled out the t terms completely, the t part completely, and we have now an ordinary differential equation. That is to say that we have an equation only in terms of the x variable. All right, that's what we've done so far, and we need to further manipulate it. Okay, right? So this equation b, right, this can be further manipulated by recognizing that omega is 2 pi nu and v is nu lambda, right? So therefore, this omega square term is going to be becoming 4 pi square nu square. Okay, I'll just write it here itself, right? And my v is going to be nu lambda. So this is going to be nu square lambda square. I write it neatly, nu square lambda square. The nu square get cancelled out, and so this is going to be minus 4 pi square by lambda square. Having cancelled it, for the sake of clarity, I will just delete the nu square completely. Okay, right? So this is just going to be minus 4 pi square f of x by lambda square. I mean, if you're taking this course online, you can just go back and then see a few minutes earlier for the expression in the previous step. It's easy to see it online, right? Okay, so you have this expression right here. Okay, now this is where we're going to do something super cool. What is it that we're going to do? This is page 4. We shall give some particle nature to this wave. How do we do this? How do we give a particle nature to the wave? Recall from the previous lecture, what were we talking about? We were talking about the de Broglie connection, right? The de Broglie relationship. And what did de Broglie say? Well, every time you have a wave, right? And the de Broglie wavelength of that wave could be connected with its momentum, right? With the momentum of the wave particle, right? By the expression lambda equals h over p or h by p, correct? Now, by using this expression right here, right? By using this expression right here, expression b, right, can be further modified as expression b. This is a very important step. B, this b over here, right, becomes expression c. Okay, And expression C is given by dou 2 f of x by dou x square is going to be minus 4 pi square divided by h square, right? Divided by p square. So this p square, I'll just take it up, right? Because this is going to be h square by p square, a by b by c, it is going to be ac by b, right? So I've taken this times f of x. Now this whole thing, right? This minus 4 pi square by h square, I'm going to be giving a shorthand notation, h bar square f of x, where h bar is nothing but h by 2 pi. I'm going to be using this shorthand notation. Okay, right? Now this is going to be called as equation C. Now, where were we? We started off with the wave equation, and the wave equation, through a series of steps, we have converted into equation C, where by our choice of the time part, we have cancelled out the time part. All right? This is what we get right now. Are we fine? So this is equation C, and this is where we are at this stage. Now, I am going to, do something strange here. See, we have this equation P right here, right? This P right here, sorry, this equation C, right? I'm going to modify this to equation D. Okay, but the only thing I'm going to do is, instead of using the variable f of x, I'm going to use the variable psi of x. I'm going to use, instead of f, the English letter f, I'm going to use the Greek letter psi. Okay, this is the Greek letter psi. Those d square psi of x by dx square is equal to minus 4 pi square p square, sorry, minus p square by h bar square times psi of x. Now, what have I done? This I've obtained by simply, replacing f of x by psi of x. This is just to indicate psi of x replacing f of x, just to indicate that my function f of x, which started off only having a wave nature, okay, right? Wave nature has been imparted particle nature too. How did we impart the particle nature? By using this step, lambda equals h over p, right? So de Broglie proposed it. De Broglie did not derive it. We are using de Broglie's proposal in our conversion of this partial differential equation into this ordinary differential equation, right? Wherein we are imparting particle nature to a wave. Okay, right? That's what we are doing. So this f of x now, hereafter is going to be replaced by this thing called as psi of x, right? And this psi of x is something understood as having both a wave nature as well as a particle nature. Please understand it carefully, okay, right? So my psi of x has both a wave nature and a particle nature, right? It is not a conventional wave nor a particle. So what have we achieved tremendously? We have achieved, right? We have achieved the original idea, which is the original objective, which is that we want to describe the motion of a wave particle, including both wave nature and particle nature. And that we have done by this way. All right. Now you may always ask me, is it a unique way of doing it? Well, the answer is of course no, but this is one of the most satisfactory way of doing it. And why? The answer I'll tell you very soon. Just hold on. Okay. So we now have this expression right here. Okay. This is going to be expression D. Okay, right? Now in expression D, wherein I replaced f of x by psi of x, right? Let psi of x be just some mathematical function, okay, right? It just incorporates the wave particle nature. That's all I'm saying about it right now. Okay, right? So we have this function, this equation D. I will delete this part now. In this equation, right? What I'm going to do is I'm going to divide both sides, okay, right, by 2m, where m is just the mass of the wave particle. Hey, now notice it. when we started off with the wave equation, right, there was no mass term involved. There was no mass term involved, right? And we couldn't do it because, a wave doesn't have any mass of it. A wave can have momentum. That's a different story, okay, right? Due to its interaction with the medium, okay? A wave could carry momentum, but a wave does not have a mass, okay? But after introducing particle nature to the wave, right, I can now define the mass of this wave particle. All right, I can now define the mass of this wave particle, and at this stage, I'm dividing both the LHS and RHS in equation D by 2m times 1 by 2m, where m, okay, right, m is mass of the wave particle. Okay, right? Are we all good? Now, after doing this and recognizing, okay, right, and recognizing that for any particle, okay, right, the total energy of any particle, total energy of any system moving along the x direction, right? The total energy of any system moving along the x direction is given by p square x, just so that the momentum is along the x direction, divided by 2m, which is the kinetic energy, right? Momentum square by 2m is going to be the kinetic energy that you can derive readily as a homework, okay, right? Plus some internal potential energy of the system, okay, right? I'm assuming that there is no other external force acting, but there is still some potential energy, intrinsic to the system, all right? So this is going to be the total energy, all right? Now, incorporating, okay, right? Incorporating this idea in this equation D, right? Incorporating this idea in equation D, right? What we're going to get is, I will give you just, like 1 minute to do the math yourself. So once we incorporate this idea into this, we shall be getting the equation of the form. This will go here. So this is going to be the total energy E. Okay, right? This is going to be E psi of x. This is, let me call this equation E. All right? Now this is a very important equation. I'll give you folks some 30-40 seconds to make this manipulation. How did this become this? This became this by recognizing that my px square by 2m or by p square by 2m, right? In this case, because the object is moving only along the x direction, right? Is the kinetic energy and the potential energy, assuming that the system has some intrinsic potential energy, okay? We're not considering any external force acting on it, okay? Right? Now the sum of these two terms is going to be the complete energy. Notice that both this and this term, right? They have an x dependence, right? But this term, this is of course going to be a function of x, okay? Right? Both of these shall have an x dependence, but the total energy is a constant due to the principle of conservation of energy, so there is no x dependence here, okay? All right. So now, how did we get to this? I'm going to put this h bar square by 2m, so that you can already see. This term is already there, right? And this p square by 2m can be written as E minus V of x. And once I put E minus V of x there, right? Then I'm going to take the V of x, I of x from this side to this side. There's already a negative sign here, so that negative and that negative will make it a positive sign over here, and my E psi of x is going to be remaining here. All right? Very simple 6th standard manipulation, right? Turning this side, that side, etc., etc. Are we good? Now this equation, okay, right? This equation is what is actually called as the time independent Can you guess? After time independent, the famous guy with the cat, the Schrodinger equation. Okay, this is what is called as the time independent Schrodinger equation. So what did we do today? We obtained the time independent Schrodinger equation, correct? We obtained the time independent Schrodinger equation as part of as part of understanding how matter, which is relevant to astrochemistry, right? We're talking about the atoms and molecules and electrons, etc., right? How they could be described using some equation, which is a Schrodinger equation that incorporates both wave nature as well as the particle nature. All right. So starting off with a very simple premise, we are here at this stage. Are we good? So we have now derived the time independent. Not derive is not the right word. We have obtained. Okay, we have obtained the time independent Schrodinger equation, right? Using a series of steps, starting off with the wave equation, right? Separating the variables, and by considering imparting particle nature by using the de Broglie relationship, and doing some algebraic manipulation. Okay. Now this particular equation, right? It can also be written more succinctly in the form. Now this expression can also be succinctly written in the form h psi equals E psi. Now we obtained it for a one-dimensional system. Okay, for a wave moving only along x direction. By simply like extending it to 3 dimensions, the same expression holds good. Only that the d square will be replaced by del square, where del is by dou square by dou x square plus dou square by dou y square. So what did we do? We got the time independent Schrodinger equation. It's of course time independent because throughout the equation there is no time dependence. Okay, right? And the toy problem, that is for the one-dimensional system, what we obtain, we can easily generalize to the n-dimensional systems also. We just have to simply use n equals 3. Okay, right? That is to a 3-dimensional system by simply extending this to include both y and z terms also. In that case, it will be a sum of dou square. We can see that in the tutorial. Okay, no big deal. But this can be readily generalized. Okay, so h psi equals E psi, where my h is going to be given as minus h bar square by 2m d square by dx square plus v of x. Now the whole thing, right, is acting on this psi of x. Okay, is acting on the psi of x, and E is a number. Now these are like mathematical operators, right? This operator, this differential operator, added to the form of the potential, whatever it is, we don't care about the exact form, right? That multiplied, that is acting on the function psi of x, which has this wave and particle nature, right? And that is going to be giving me back one number, E is a number, and psi, okay, right? Psi is this mathematical function, okay, right? Psi is a mathematical function which, psi is a mathematical function which is given a special name, okay, right? It's given a special name called as the wave function. All right? So please understand this. So the psi of x is what is called as a wave function, and that is obtained simply as a solution to some mathematical equation. All right? So I want you folks to, wherever you are, right, in whichever part of the world you are, kindly repeat after me the whole thing, the whole exercise, okay? Now what I'm going to tell is extremely important. The wave function is merely a mathematical solution. The wave function can never be obtained as an output in any experiment. Please, I want to emphasize this point. Now finally I can delete this original starting point, and I want you folks to understand that the wave function psi of x, or for a more general case, right, for a 3-dimensional system, psi of x, y, z, right, can never be obtained as an output in any physical experiment. This is an extremely important point. It is purely mathematical. It is this is an extremely important point, and please pay attention to this. Okay, right? Now, the reason why I'm emphasizing upon this point is that the phrase wave function is very hyped up. Typically, even non-scientists, like typically use this phrase, and they attribute it to several interpretations, etc., etc. Well, there are of course several interpretations of the wave function amidst physicists. Okay, right? The one that is most amenable to us for astrochemistry is what is called as the Born interpretation, the probabilistic interpretation, which is very useful in chemistry and astrochemistry. Okay, but we're not going to talk about that. But ultimately, the wave function is a purely mathematical entity. Okay, you do not get it as an output of any experiments, and that is the specialty of this equation and the solution to it. Okay, right? Whereas the energy is a number that is physically observable. Okay, right? It's a number which has units, of course. A number with units. Okay, and it's physically observable. Okay, right? This is not. The wave function is not physically observable. Okay, so this is a mathematical recipe. This left-hand side is a mathematical recipe, right, to get the energy that can be compared with experiments. All right. So what did we see in today's lecture? We saw that we can start with the wave equation. We can use various assumptions, and then we could convert it to the partial differential equation could be converted to an ordinary differential equation. And in that ordinary differential equation, right, we could impart particle nature to the purely wave equation, right? And so we deal with wave particles. We could introduce the mass of the wave particles, and from that we obtain what is called as a time independent Schrodinger equation, right? The solution to which will give us the energy of the system, okay, the energy of the quantum mechanical system, right? And as part of it, we've also, the solution to this differential equation is what is called as a wave function, which is a purely mathematical entity. It can never be physically obtained. So these are the points I want you to note from this lecture, and the relevance of this equation in astrochemistry will be further explained to you in the next class. Thank you so much.